So let's talk about linear motion. It's called linear because you only keep track of one dimension, either your height or your position along a line or position along the bank of a river or something like that. When we use the standard position equation, we are assuming that you are falling in a vacuum with no friction, which is kind of a big assumption, but we're starting modeling with some basic assumptions to make our life easier. We also assume that acceleration due to gravity is constant. I did not realize that it was not constant until I started teaching, and I read in a book somewhere that it said, oh, by the way, it's not actually constant. We just assume it's constant to make our life easier. Well, shit, I wish I'd known that before. That still pisses me off 30 years later. Anyway, I digress. Using this position, the first equation, S of t is in feet and t is in seconds. The position equation is negative 16t squared plus v naught t plus s naught. V naught is initial velocity and S naught is initial position. Taking the derivative, we get velocity, negative 32t plus V naught. Taking the next derivative, we get acceleration, which is negative 32. So in this scenario, when we're using feet and seconds, acceleration is a constant, sort of constant, negative 32 feet per second squared. In the other scenario, we use meters and seconds. Here we have the position is negative 4.9 t squared plus v naught t plus s naught. The first derivative is negative 9.8 t plus v naught, and the third derivative is negative 9.8. So in metrics, acceleration is a constant, negative 9.8 meters per second squared. So let's play with some examples. Here we have Ethel threw Fred off a 200-foot building. She's very strong, so she was able to throw him up and over the edge. Fred's position at time t is given by S of t is negative 16t squared plus 32t plus 200. Taking the derivative, I find the velocity, his velocity is negative 32t plus 32. So his initial position is 200, which makes sense. He's on top of the building. That's 200 feet. That's where he started. That's where time starts. His initial velocity is 32 because I see that in the equation, 32. So that means Ethel was able to throw him up at a velocity of 32 feet per second. She's kind of strong. She scares me. So what questions do I want to ask? How about when he hits the ground? Well, when he hits the ground, position is 0. So I'm going to take S of t and set it equal to 0. Solving this using the quadratic formula, I get t equals negative 2.67 and 4.67. I don't use the negative number because that's like when he's walking up the stairs. That's before time starts. When we model, we have to assume certain things, like we're throwing things in a vacuum. We also assume time starts at 0. So this is modeling his position after time has started. He hits the ground at 4.67 seconds. What is his velocity when he hits the ground? I'll plug that into velocity and I get negative 1.17.44. Another question I might ask is, if she's throwing him up and over, what's the highest point that Fred reaches? Well, let's try that. At the highest point, his velocity has reached 0. So he has a positive velocity while she throws him, and until he slows down and gets to his highest point, at that point his velocity is 0, and then his velocity starts becoming negative because he's falling toward the ground. Velocity tells me the direction, negative means toward the ground. So let's set velocity equal to 0. Solve this, I get t equals 1 second, which means he hits his highest point at 1 second. What is that highest point? Well, I stick it into position and I get 216. So that means Ethel threw him 16 feet up in the air. That's not very realistic, but it makes for a good word problem. What if instead of throwing him off, she just pushed him off? How does that change our equation? Well, if she just pushes him off, his initial velocity is 0. So I have negative 16t squared plus 200. I can still ask when he hits the ground, and I get t equals 3.54 seconds. I can still ask what his velocity is when he hits the ground. So I plug that into my velocity equation, negative 32t. So Fred's velocity when he hits the ground is 113, actually, he hits the ground going 113.28 feet per second. His velocity is negative 113.28. The negative tells me he's going down into the ground. Let's try something other than this particular standard position equation. Let's try a funky position equation. We've got Superman. He's flying off in the air. His position is given by negative t cubed times t minus 4, where the position is given in meters and t is given in minutes. So his flight looks something like this in terms of height. So what do I want to know? I want to know how high he goes. So that means velocity is equal to 0. My velocity for this equation is 12t squared minus 4t cubed. Set it equal to 0 and factor. I see that I have t equals 0 and t equals 3. Well, t equals 0, he's still on the ground. He hasn't gone anywhere yet. That's not going to happen. This is what I'm interested in, this point up here, the top of my hump, where t equals 3. I put that in the position equation and I get 27, which means after 3 minutes, after 3 minutes, Superman has reached his highest point at 27 meters up. Next question might be, what is his velocity when he hits the ground? So I need to find out when he hits the ground. I set position equal to 0. I see I have t equals 0 and 4, which makes sense. He starts on the ground. After 4 minutes, he hits the ground again. Putting 4 into velocity, I get negative 64 meters per minute. So his velocity is negative 64 meters per minute when he lands after 4 minutes. So when we study linear motion, typically we use S of t to stand for position. But you have to remember, we only know what's going on in one dimension. The derivative of position is velocity, which is denoted v of t, and the second derivative of position is the derivative of velocity, which is acceleration. The highest or lowest point, or furthest left, furthest right, depending on the extreme of position, is given when the velocity is equal to 0. The thing that's moving hits the ground when S of t equals 0. So we'll practice more of these in class, but make sure you learn this formula. But other than that, these are pretty straightforward.